What's up guys, this is Friendly Developer here. Today I'm here to talk about trees. Tree is a type of data structure which is asked a lot in interviews. There are a lot of tree problems, very important. This is a very important data structure. It's used wherever there is a hierarchical level of hierarchical way to access certain elements. Let's start with very basic how we represent the tree and how each node is represented, and let's solve some basic problems and let's see how we can think in terms of how intuitively we can think of trees to solve basic problems. Okay, so let me write a basic very simple tree. A tree is a collection of nodes, okay, linked in certain way. If you have used linked list while you are programming, then you would know that a linked list will contain some data. A linked list, I'm just representing something 1, 2. Let's say this is a linked list. Each node will represent some data and it will have references to other nodes. Okay. Usually in a single linked list there is only one link or one reference. Here in a tree we have, for considering a very simple binary tree, we have two references. Okay, one is to its left child, one is to right child. For every node there is a left child and right child. Okay, now coming to basic terms present in related to tree concept. The starting node is called the root node. Okay, and the node which do not have any other children are called leaf nodes. Okay, and a node which is not leaf is called non-leaf node. And okay, so if we see how these nodes are actually represented in memory, then the root node's data would be 1. Root node's left reference would contain the address of this node. Okay, node which has the data 2. Similarly, the right reference, this reference right would contain the reference to the node which has the data 3. Okay, this is the memory representation, how it is represented. Now let's this is just about trees. Representation is pretty easy, but what's important is how we solve the problems. Okay, so let's look at basic problems on trees. Okay, let's start with this. Find the number of nodes in the tree. Okay, in the next video I'll be implementing all these problems in C++, and in the implementation part it would be clear if you understand intuitively how we can relate the solutions for small problems to solve the bigger problems. I'll explain what I mean by that. Okay, so given the problem, let's take this problem. Find the number of nodes in the tree. Okay, so let's consider this tree. Now you can see that the number of nodes is 1, 2 and 3. Let's write a bigger tree. Here the number of nodes is 1, 2, 3, 4, 5, 6, 7. Okay, the first thing that you should do whenever you are given a tree problem is just assume that you have the solution. This is really important. This can help you a lot while solving tree problems. So, here's the way to think of it in terms of easier way. Okay, see, first assume that you have the solution to your left subtree. Solution to this problem, number of nodes in the left subtree and the number of nodes in the right subtree. Then given the solution to number of nodes in left subtree and right subtree, how do you find the solution to this whole tree? Okay, given the solution to smaller subproblems, how do you relate that with the current node such that you get the solution to this whole problem? So if you if I want to show you what I mean, number of nodes in the left subtree. Let's say I start by looking at the current node, okay, root node, which is my current node. Here, let's assume that you already have the solution, that is the number of nodes in the left subtree, which is 3. Assume that you already have the solution to the number of nodes in the right subtree, that is 3. Okay, now given these two solutions, what is the number of nodes in the whole tree? The number of nodes in the whole tree would be 3 plus 3 plus 1. What is this 1? 1 is including the current node. Okay, so we observe that given the solution to left subtree and right subtree, it is very easy to think of the solution to this very large problem. I am explaining this because when we are solving tree problems, sometimes I find people find it a lot difficult to visualize recursion. So this kind of logic or intuition can help in figuring out the solution. Okay, now let's actually solve this problem. So find the number of nodes in the left in the tree. Let's say we have a function which takes the root node of the tree as input. What should we find? We should find the number of nodes from the tree whose root node is given. Okay. So how do we find? We assume that we already have the solution for left subtree and also right subtree. So how do you do it? Your function will return the number of nodes in the tree. So what you do is, say in the left you have number of nodes in the left subtree. You send the left subtree's address to your function. You assume that it is already, your function is already working correctly and it's giving the right solution. So this will solve and store the number of nodes in the left subtree. Similarly, it will find the number of nodes in the right subtree. Now what do we do to find the solution to this whole problem? We sum these two solutions and add 1 to this, because the current node is also considered. So we just return left plus right plus 1. This is how we solve this problem, but the assumption that we did was our function is already working. So that's how we thought initially. Our function is already working and we store the results of solving the problem for left subtree and right subtree and add 1 to this. But actually our function is not working because we still have to write the base case. Okay, so given any such problems, there are a lot more similar problems. You need to think of it in the same way. Okay, you find a solution to left and right subtrees and you just have to figure out how you will link that solution with the current node. Okay, and after that you just need to write the base case. To find the base case, you just consider the simplest tree. The simplest tree could be, a tree with only one node. This tree has only one node, that is 9. Consider this tree, its left and right children will be null. Okay, simply null. Or if you are using C++ or something, it will be 0. Okay. We just write the base condition, that means write the case considering the simplest tree. Okay, so if my root node is null, if the node whose number of nodes I am finding, if it is null, then I return 0. Because if I have been given a tree which doesn't have any node, or if its reference is pointing to null, then there are no nodes, so I just return 0. Now this will solve the entire problem, because see, if I give this node as the input to my function, then 9 is not equal to null, so it will find the sum of number of nodes in the left subtree. This will return 0. This base case will run, which will return 0. So left will contain 0. Similarly, 9's right child is sent to the function to find the number of nodes, which will again make this base condition as true, which will return 0. So 0 plus 0 is 0 plus 1, the current node, this will return 1. So given any bigger tree, this is how you can trace the solution. You can trace the solution to this bigger tree. Similarly, this given this bigger tree, consider that you are sent this node, that is 1, to your function to find the number of nodes. Now what you will do, you will store the result of left subtree and also right subtree, and you will add those results and add 1 because the current node is also included in the node. Okay, so this is the kind of intuition. I know this is a more unnecessarily fine-grained, detailed way, but if you can understand this relationship between how to get the smaller subproblem solutions and how to relate it with the current node that you are looking at, then a lot of tree problems become very easy. Okay, now let's find a solution to other problems which is also really similar to this pattern. Okay, let's see the solution for other problems, and let's apply the same kind of pattern that we saw now. That is how we can find use the solution that we already have of left and right subtrees and link it with the current node that we are looking to find the solution to the whole problem. Okay, so find the sum of nodes is the problem. Let's say our function gets the root nodes reference. Now applying the same logic that we wrote earlier, let's assume that our function is already working and it sends you the solution to, it sends you the sum of all nodes in the tree. Already assume that it's working, and so what you will do, you will store the result of left subtree and right subtree. You will call your function to find sum of left subtree's nodes and store it. Similarly, you do this for right subtree. Now what you will do, you just need to see how the solution to left and right subtrees, how you can link that with the current node. Okay, let's say I sent this tree to my function. This tree means its root node will point to this node whose data is 1. So given the sum of left subtree and sum of right subtree, what is the sum of left subtree? 2 plus 4, 6 plus 5, 11. Sum of these two is 10. Okay. Given the solution to these two, how can we relate it with the current node to find the solution to the whole problem? What is the whole problem solution? To find the sum of all nodes in the tree. So sum of left subtree is 11, right subtree is 10. The total solution is 11 plus 10 plus current node's data. Okay, so I just return the left subtree's sum plus the right subtree's sum, which we have got by calling our function, and the current node. The current node is this node, current node's data. Okay, so once we do this, our problem is solved, but the only case that is left out is the base case we have to add. How do you find the base case? Just apply the same function, apply your function for small problem. Consider a small problem, that is a small tree which has only one node. Okay, its left and right subtrees will be null. So what is the sum of the this tree? The sum of this tree is 1. Okay, if you are given a node which doesn't have any node, I mean if you are given a tree which is null, that means if root is null, if you are given a tree like this, then its sum would be 0 because there are no nodes, so there is no data, the sum is 0. So if you just apply this your function to this tree, let's see, I give 1 to my function to find the sum. Now root is null, no, root is not null because I have a node 1 which is not null. Then I go for finding the solution for left subtree and right subtree. The sum for left subtree and right subtree, both these recursive calls will make this base condition as true. So 0 is returned. This call will return 0, this call will return 0. So left and right both are zeros. So what is the solution to my bigger problem? The solution is left subtrees and right subtrees sum plus the current node sum. Current node sum is 1. So 1 is returned. So that is how we can think of this problem in a similar way. Similarly, if we consider this third problem, that is count the leaf nodes. Okay, assume that I'll change the function name to count. Okay, count. Here also, how can we, assuming that you already have the solution to left and right subtree. Let's say there's a leaf nodes. These three are the leaf nodes. Number of leaf nodes in the left subtree is 2. Number of leaf nodes in the right subtree is 1. Okay. Now, what is the solution to the whole problem and how we can relate it? That is the only thing that you need to worry. So, assume that your function already gives the solution, just like how we did earlier. That is, count the number of leaf nodes in the left subtree and count the leaf nodes in the right subtree. Count the leaf nodes in the right subtree. Now, how do you relate it with the current node? Okay, let's erase this base case. Okay, how do we relate it with the current node? You know that current node has a child, okay, has at least one child. It has two children, that is this subtree and this subtree. So we know that this is not a leaf node, so we do not consider this as the leaf node. So how do we relate it with the answers that we found? How do we relate it with the subproblems of left and right? We'll return left subtree's leaf count plus leaf count in the right subtree plus 0, because the current node has both left and right children. That is not null. Okay, the base case that we need to consider here is, consider the same small subproblem, that is this node which only has 1 as its node. Now I send 1 to this my function. Now let's see, once left node is 0, once right node null, once right node is also null. So this is my leaf node. So that is the base case. So what I will do, I will simply check if the current node's left is null also, and the current node's right is null. Okay, if this is true, then that means we are looking at a leaf node, so we just return 1. Okay, this is the smallest problem where we need to find the base case. Okay, once we find this, assume that let's say my root node itself, somebody gives an empty tree. Let's say root node could be null. So I need to add one more base condition. If root itself is null, then anyway there is no question of number of leaf nodes, so I just return 0. Okay, this case is also helpful if you have a tree something like this. Only one node is having a child, the other is not having a child. So in this recursive call, root dot right would be null. When your function is called, root would be null. So 0 would be returned here. Okay, so this is how if you can trace the same kind of logic, whatever we did earlier, the same pattern holds here. Similarly, to find non-leaf nodes. Okay, so here also, let's say we apply the same kind of pattern to find non-leaf node. Instead of 0, the current node that we relate is 1, because this node 1 will have both left and right children, assume that. So we consider this also as the non-leaf node. We are solving the problem for number of non-leaf nodes. So given the solution to smaller subproblems, we have found this. The only thing that is left is base condition. How do we find the base condition? Given a tree which is empty, then what is the number of non-leaf nodes? Since there are no nodes, there is no question of number of non-leaf or leaf nodes, so I return 0. Now in this case, instead of returning 1, see, if my nodes left and right children are both null, that means if it doesn't have any children, then this is the leaf node. So number of non-leaf nodes is 0. So I just return 0. As you saw, if you think of tree problems in a recursive way, that is, assume that you already have the solution to smaller subproblems, that is left and right subtree. You just have to think about how to relate those solutions to the current node. Okay, once you do that, all tree problems are very easy to solve. At least a certain set of problems are very easy to solve. Okay, we'll look into more complicated problems in further videos. Anyway. Similarly, to find the height of the tree. Okay, so to find the height of the tree. The height of the tree, given a tree, the height of the tree is the height of the root node. Okay, what is the distance of the root node from its lowermost descendant or lowermost child? Okay, so this is the root node. Now let's say my tree is something like this. Height of my tree is 1, 2, 3. Okay, because its lowermost descendant is 6, which is at a distance 3. So here also we can apply the same pattern that we found earlier. Given the solution to, assume that you already have the solution to your left subtree. That is, what is the height of left subtree? This tree, 1, 2. 2 is the height. And what is the height of this right subtree? 3 is at a distance 1 from its lowermost descendant. So its result is 1. Assume that you already have the solution. Now how do you relate it with the current node? How do you relate these two solutions with the current node? See, to find the height, what you do is you find the distance from the lowermost descendant. Okay, the lowermost descendant could be at the right or could be at the left. So what you take is you take the maximum of these two solutions. Okay, maximum of these two. That means this subtree is having the maximum height and right subtree is having lesser height. So you take the solution height of your left subtree and add 1. Okay, why add 1? Because this constitutes to a height of 1. Okay. Now once you add 1 to the maximum of these two, you find the height of the whole tree. Now how do you implement the same using your function? Let's say your function is to find height. What do you return? You return maximum of height of left subtree and whatever is maximum of height of right subtree, whatever is maximum, plus 1. Okay, plus 1 because considering this, whatever is maximum we just return plus 1, and here also we write the base case. If my root is null, then I just return minus 1 because given a tree with a single node, its height is 0. Okay, this is by convention, but sometimes people also take this height as 1, but this is usually the case. Any tree which is having only one node, its height is 0. So if I have been given a tree which doesn't have any node, we'll take the height of that tree as -1. So my height of left subtree, if I send this tree to my function, its left subtree side would be -1. Similarly, its right subtree side would be -1. Maximum of -1 and -1 is -1. -1 plus 1 is 0. So height of this tree is 0. Similarly, we can apply the pattern that we saw earlier to bigger problems. Okay, this is certain number of basic problems that you can commonly find in a lot of interview questions, in aptitude questions, if there is programming involved. And we'll look into a lot more complex problems in future in further videos. Hope you guys found this way of approaching tree problems useful. Now in the next video I'll show you the actual implementation, which will have a lot less code, and it will be more fun to actually code it out. So thank you. Please do share, like and subscribe. Thank you. See you next time.